Hello, everybody. Welcome to this super fast course on linear regression. Now, this course is designed to take people who maybe have only really dealt with linear equations, like maybe in high school, and aren't really into all this stuff, and just kind of guide them through, hopefully, all the different ways that we use linear regression these days. So we'll talk first about what a linear equation is, then we'll get into why you might want to use linear regression. We'll talk about a few different ways that the model is normally fit. Then we'll go into ordinary least squares regression, all right? The most common way of fitting a linear regression model. We'll talk about drawing statistical inference, which is super important if you ever want to do any kind of quantitative research. I mean, it's what basically all branches of quantitative research. If you're going into a master's degree or a PhD program, you will need to learn specifically that section. We'll talk about interpreting the results. We're going to see some examples in Python. We'll talk about a couple of different ways other than ordinary least squares to fit the model. Then we'll discuss some of the weaknesses of linear regression, especially overfitting, which we will describe later, and how we might combat that using regularization techniques. That's a machine learning term. You will see that later. And we'll go all through. Once we've got through everything and you've seen how to do it all in Python, we're going to talk specifically about applying it in finance. Now you should see in the description below times, and it's all split into chapters. So if you're really only interested in the quantitative research part, say you're studying education at the master's or PhD level, and you only want to know how to do linear regression in order to draw that kind of inference, you can just watch those parts, ordinary least squares through OLS and Python. And that should teach you plenty about how to actually run that kind of inference. And if you want to know it all, if you're into machine learning, I would watch everything other than the finance applications. And if you're into machine learning and finance, or if you're into portfolio management, any kind of financial stuff, definitely watch all the way through the finance applications. Now, including this video, this is 3.5 hours of content. So it is a lot. Probably don't want to do it all in one sitting, but we go through it all. You guys ready to get started?
So by the time they're done with high school, pretty much everybody has some experience with linear equations. And you can see on our graph, we've got a linear equation that forms this line right here. Now the most famous form of linear equation is y equals mx plus b. This is how we usually talk about it in high school. And in this, m is the rise here over run, also known as the slope, and b is the y-intercept, which is the point where that line crosses the y-axis right over there. Now, y equals mx plus b is how we talk about linear equations in like high school or maybe college algebra, but as we get more advanced in linear algebra or machine learning or portfolio management, the terminology changes a little bit. So what we're going to do now is we're going to walk. We're going to walk step by step from y equals mx plus b to the way we're going to talk about linear equations for the rest of the course. And we're being very meticulous here to show that linear equations are the same even when they're more complicated. So we're going to start just by changing a letter. What we have right now is y equals mx plus b. And we're just going to change letters. Instead of m, we are going to write a, and instead of b, we are going to write c. So we have y equals ax plus c. Now this is exactly the same equation. We've just written down different letters. And a and c are just arbitrary numbers that don't matter, so we haven't changed anything yet. Now we're going to multiply both sides by b to give us by equals, sorry, my mistake. We are being very meticulous here. B times ax plus c. That's going to give us b ax plus bc. So now we have by equals bax plus bc. But again, a and c are arbitrary, so we're just going to let them absorb that b to give us by is equal to ax plus c again. And now we want to get everything on the same side, so we're going to subtract the by over to give 0 equals ax minus by plus c, but because b is arbitrary, it can absorb that minus, and we end up with ax plus by plus c. Now we're going to change letters again. Instead of writing instead of writing c, we'll start with c, we're going to write a naught. So this goes over here. And instead of writing a, we're going to write a1. And instead of writing x, we're going to write x1. And instead of writing b, we're going to write a2. And instead of writing y, we're going to write x2. So this is exactly the same equation as before. We've just changed the letters that we're writing. And now we have a naught plus a1 x1 plus a2 x2 equals 0. But what if that's not equal to 0? It can't be equal to 0 everywhere, right? So if we have now a naught plus a1 x1 plus a2 x2 equals y, well, we can repeat all of the same steps that we did before, and I would like you guys to try this on your own. All right? Do the same steps as before, and when you're done, we should end up with a naught plus a1 x1 plus a2 x2 plus a3 x3 is equal to 0. And once you can do that, you can see that we can do this as many times as we want until we end up with something like a naught plus a1 x1 plus a2 x2 plus whatever plus a sub n x sub n equals 0. Or if we want to be more concise with our notation, we could say a naught plus the sum from I equals 1 to n of a sub I x sub I is equal to 0. And that's great. You might see something like that in a lot of maybe linear algebra books or things like that. But in finance, especially in quantitative portfolio management, they'll just usually use Greek letters instead. And we would normally write in portfolio management, I'm going to write here, quantitative portfolio management. You'll see people write alpha plus, here's the sum from I equals 1 to n of beta sub I x sub I equals, well, it's usually equal to y over here. And in portfolio management, y would usually be the returns, and x would be some factor or source of risk, and alpha would be the returns that are independent of risk. But we are going to talk more about using linear equations for portfolio management later on in the course, so we're not going to worry about that too much right now. We're still working on the form of the equation. Right now we're at alpha plus the sum from I equals 1 to n of beta sub I x sub I is equal to y. But if we can unpack this, right, is beta 1 x1 plus beta 2 x2, and so on, which is actually the same if we have these in vector form, beta 3 all the way through beta n, and we're multiplying that by a column vector of x1, x2, x3, all the way down to xn. These two are equal to each other. So in vector form, we could say alpha, this is just a scalar, all right, it's a single number, plus beta, which is a vector, times x, which is also a vector, is equal to y. And if you want to get really, really concise, which we do here, if you were to have a or alpha be a part of this vector, let's put alpha in there, alpha, and 1 as part of this vector, well, you could put alpha inside that beta. So now we just have beta x is equal to y. And alpha is inside this vector. And this is the form that we're going to talk about. It's actually a lot easier to do a lot of the calculus and algebra stuff that we need to do if we just keep it in this form where these guys are vectors. But let's skip down and look at some actual data that I have on a plot here. And as you guys can see, this data is not at all along a straight line. So what we're going to do with linear regression is we're going to find a line that is closest to all of these points. Let's just kind of draw a line to see what that might look like. Maybe something like this looks pretty good. And if we were to run a linear regression, we would want a line to look like that. But as you can see, the points are not on the line. And we will talk about this more later. So what it looks like really is that our data is from a straight line. I don't want the word straight. It's from a linear equation. How about that? Linear equation, but with randomness added. Random, there we go, randomness added. So what we're going to say is the function that our data actually comes from, I'm going to write this the generation function, or generator function. It actually looks like the data comes from beta x, where these are vectors, plus epsilon, where this is some random error. You usually hear it referred to as error. And this error right there accounts for the distance from the line for all of these points. And so this equation over here, y equals beta x plus epsilon, that is the function that we're trying to figure out using linear regression. Specifically, linear regression is all about estimating beta. We've really got to talk about the limitations of linear regression, and especially the biggest limitation, which is that the relationship between the independent variables and the dependent variables is linear. All right? So let's say you have one independent variable and you plot your data and it looks like this. Well, linear regression would actually fit this pretty well because that relationship looks like a straight line. We'd have something like this. And our model, of course, would be y equals beta x, or y equals beta x plus epsilon, whichever way you feel more comfortable writing it. So that's great, but what if you plot your data and it looks like this one? Now we're no longer straight. Actually, it looks like a quadratic equation would fit that pretty well. Well, if we plot this data on a log scale with base 2, we would get a straight line. So we can just transform our independent variable, and instead of y equals beta x, right, we would get y equals beta x squared, or maybe even y equals beta 1 x squared plus beta 2x, something like this. But we can do that transformation because you can just take your x values and square them to get x squared, and then create a linear combination of those quadratic and linear values. So, even though we aren't really talking about it that much, the idea behind using a transformation to make the relationship between variables linear is a big deal. And a lot of times there is a transformation that will work. This was a pretty simple one where we can see that the transformation that's going to work is going to be something like x squared. It's also really common to see ones where the transformation that will work is the natural logarithm, which might have worked for this one as well. Now, what if your data looks like this? Well, this is really a circle, isn't it? Now, there's no way that linear regression can ever fit a circle, but in this case, we could, all right, I'm putting could here because it is a lot of work, we could transform to polar coordinates. And do linear regression on the polar values. Like I said, that is a lot of work. It's kind of a big deal. It's pretty cool though if you want to try it out. Now lastly, this one has no discernible relationship. They're just kind of all in a big splotch right here. And a line of best fit might look something like this. But that sucks. It really is not a good description of the data at all. And a lot of real world data, a lot of naturally occurring data ends up looking like this, just kind of a blob. So the necessity that the relationship between variables be linear is a big obstacle for linear regression models. And there are a lot of machine learning models that don't have that problem. Now this makes linear regression particularly poor at prediction relative to other models. So why would we use linear regression at all? And the reasons really stem from classical statistics and experiments. Namely, there are a few assumptions, and if we make these assumptions, we can draw statistical inference about our variables using linear regression. And most quantitative fields, most quantitative research actually in all fields, I mean like education, economics, communication, biology, whatever it is, all kinds of fields, use this particular technique. All right, they can draw statistical inference from linear regression, and that is why linear regression is so important. And we're going to talk about that a lot more throughout this course. But I just want to make a list of reasons to use linear regression. And number one, statistical inference. Absolutely. I'm going to put it in all caps right here. Now, there is some debate among data scientists if statistical inference is really worthwhile. But in all kinds of academic studies in all fields, like I said, they're going to use linear regression specifically to draw statistical inference. Now, number two, linear regression is easy to explain. Most people, by the time they get through high school, have some experience with linear models, all right, y equals mx plus b, and they kind of understand what, or can visualize what linear regression means, what it looks like. So it's really easy to explain even to non-technical people. Another reason you might use linear regression is that the coefficients are meaningful. And this comes from slope, which again people are generally used to thinking about by the time they're done with high school. Whoops, that says models. Meaningful, I mean to say. So the coefficient here, say beta x, really tells us that for every 1 unit increase in x, we can expect a beta unit increase in y. So coefficients are meaningful, and that is very important in, say, business context. And the last reason is that linear regression actually scales well. When handled properly, linear regression is very stable. So you can scale it to big data, and it also handles high velocity data, which means it's data that's generated quickly, really well too. So these are the 4 reasons why a person might use linear regression rather than a more powerful machine learning model. So we know we want to fit a linear regression, and we know why we chose this form of model, and we're ready to fit it. So how? How can we actually fit the model? Let's look at it again. We're saying that the data is generated by this function y equals, sorry about that, now beta x plus epsilon, where this is the error here. And our model actually looks like y hat is equal to beta x. Now, the difference here is this epsilon, that error. And if we subtract the model prediction from the actual value, all we'll have left is the error. See, that's beta x plus epsilon minus beta x. Cross those two out, and we just have epsilon left over. And to get the best model, we really want to minimize this error. And there are a lot of ways to measure the error of a model, but there are two methods that are really by far the most common. Now, first one, absolutely the most common way to handle fitting linear regression is called the root mean squared error. And we'll just walk through kind of deriving this. So let's start with the error. And we know that that's equal to the actual values minus the predicted values. And we're going to square them to make them positive. And we're going to get the mean by summing it all up and dividing by the number of observations. And then we'll take the square root, and the square root, all it does is return the error, or the average error, the root mean squared error here, back to the same scale as the y values. So our RMSE, root mean squared error, is going to be the square root of the mean, I equals 1 to n, of the errors squared. And what's great about this one, the reason why it is so popular and it's used all the time is we can actually solve this using the first derivative. We can actually minimize this, by first derivative. Just like you might have done in Calculus 1. And we're actually going to do that in the very next section. Now, the second most common way to fit a linear regression is, or to measure the error of a linear regression, is called the mean absolute error. And this kind of follows the same general concepts as the root mean squared error, in that we're going to get the error, we're going to make it positive, we're going to take the mean, and then we're going to make sure that we're on the same scale as the y values. So let's start by getting the error, difference between the model and the predictions, and we're going to make it positive this time just using the absolute value, and then we'll get the mean here. And this is actually already on the same scale as the y values, so we're done. So the formula for the mean absolute error is just the mean of the absolute errors. Very simple, right? Now, to fit a linear model using this measure of the error, we actually can't take the derivative because absolute value is discontinuous. It's a discontinuous function. So we're going to have to solve this one numerically, and we'll typically do that with a technique called gradient descent, and we're going to look at how to do that just a little bit later. But lastly, I want to talk about a third way to solve the problem of linear regression and get the best possible value of beta. And that is called maximum likelihood estimation. And this is very different from the others, but it's also really cool, and it's an incredibly useful thing to kind of know throughout statistics. And the idea here is that we want to find the value of beta. Okay, we want to find beta such that the probability of getting our data, given that our model is real, I'm going to write given the model, is maximized. And like I said, it's really very different. The way we're going to handle doing that is going to involve derivatives and stuff, but it's a little more complicated. And it definitely sounds complicated right now, but honestly, it's not very hard in practice, and we're going to see that soon after we talk about a couple of other things. The most common way to fit a linear regression model, and the one that we can use for statistical inference, is called ordinary least squares regression. Ordinary least squares. Or you might just see it called OLS, or you might just see it called least squares by itself. And it's really all about minimizing the root mean squared error that we saw before. Let's write that down. Root mean squared error. And it looked like this. We found the error by doing the predicted minus the actual values. We squared it. Then we found the mean here. And then we take the square root. So we want to minimize this, but it's actually going to be a lot simpler than it looks. So to start, we've got the RMSE, and we want to minimize it. I'm going to write this again. We want to minimize the square root of the sum of the errors here, squared over n. But if you think about it, the square root is a monotonic function. The plot of it looks like this. It is always increasing. So we really don't have to care about that square root at all, and we can really just minimize here the mean squared error. The mean squared error there. But if you look at this n, this is just a constant, and it's not really affecting the minimum at all, so we don't need to worry about it either. So we really just need to minimize the sum of the squared errors. Sum of the squared errors here. And that is why they call it least squares, is because all we actually need to minimize is the squares. All right, so let's deal with this in vector notation. Okay, so we know that y hat is equal to x times beta. So if we look at this in vector notation, we want to minimize x times beta minus y squared. Oh, sorry. In vector notation, you can't just do squared. And I actually want to rearrange those. So I'm going to do this instead. I'm going to say y minus x times beta transpose times y minus x times beta. Got to do this transpose thing because we're talking about vectors now. And you can't just square a vector. It doesn't really work out if you guys are familiar with linear algebra. So we can actually take the derivative of this. All right, this is our sum of squared errors. We can take the derivative of that with respect to beta. So I'm going to write this here. The derivative with respect to beta of the sum of squared errors. Now, this is some pretty simple vector calculus. It's really simple, really similar to y minus beta x squared if we weren't talking about vectors, if everything was a scalar. So when we take the derivative of this one, what we're actually going to get is just negative 2 x transpose times y minus x beta. And we can find the minimum just like we would in like a beginning calculus class. We'll take this derivative and set it equal to 0. Negative 2x transpose times y minus x beta is equal to 0. And now we just want to solve for beta. So you can see the 2 is not going to make any difference there. Now we can't just move x transpose across because these are vectors. So let's multiply it through instead. X transpose times y minus x transpose times x times beta. order matters, all right, when we're dealing with vectors. Let's go ahead and move that to the other side. X transpose y equals X transpose X times beta. And now, I'm rearranging a little bit. We're going to have X transpose times X inverse times X transpose Y. So finally, we've got it. All right, I'm going to call this version of beta beta hat. Okay, note the hat, because this is the most efficient estimator according to the Gauss-Markov theorem. And we aren't going to discuss what that means exactly, but just keep in mind that that is usually a good thing. All right? So let's have a look at this. Our beta hat is equal to X transpose times X, the inverse of that, times X transpose Y. And if we can play it just a little kind of fast and loose with the vector, with the rules of vectors, just to get kind of better intuition as to what's happening in here, we can write that as X transpose times Y over X transpose times X. So let's look at the top here. And X transpose times Y would actually give us the covariance between our independent variables X and our target variable Y. Whereas on the bottom, that X transpose times X would give us the covariance between all of the independent X variables. So as you can see, our estimator for beta, okay, the most efficient estimator, beta hat, is really like a ratio between it's a ratio of covariance between the independent variables and the target variable to the independent variables' covariance with each other. And this is really one reason why it's important that the independent variables not be highly correlated, because they make really weird stuff happen in this ratio that kind of throws the whole thing off. All right, now that we have beta hat, we're going to use that statistic to draw some statistical inference. So let's remember that our model is y hat equals beta x, or y equals beta x plus epsilon, depending on what you how you like to write it. So we're actually going to need a few assumptions about the behavior of the data in order to draw inference. And our assumptions are going to be number one, all right? Number one assumption is that observations are independent. So we need all of our data points to be completely separate from one another. Like, for example, we couldn't take two temperature readings in the same place and at the same time and then treat them as separate observations, because they clearly aren't separate, right? I mean, the temperature is not going to be very different. So this assumption is typically more about how the data was collected than anything we can really do after collecting it. Assumption number two is that observations are homoscedastic, which I hope I am spelling right. I'm pretty sure I am. All right, and what this means is that any group or subgroup, I'm actually going to write this down, any group or subgroup of observations will have the same variance. And mathematically here, what we're going to actually translate this to is going to be the variance of y given x is equal to sigma squared, which is a constant. All right, it doesn't depend on x. Very important. And number three, we are going to assume that observations are normally distributed about the mean. Another way of saying this is that the errors are normally distributed. So our errors are epsilon. So we're going to say that our errors are normally distributed with mean 0 and some sigma squared, sub epsilon there. So really, if we put all of this together, we are assuming that y values are independent. And that y is normally, y given x is normally distributed with mean beta x and variance sigma squared. Okay, so we are making this very strong assumption about what distribution our data actually follows. And while there are tools to investigate these assumptions, most of them are not very powerful in a statistical sense. And so really our best course of action is to fit the model and then check these assumptions on the residuals. And typically we're just going to be looking at plots to check them. However, sometimes that's difficult or impossible to do afterward, depending on what kind of technology you're using. So normally the sorts of things that I would do if I were trying to run some statistical inference, I would run a box plot, and here we'll draw up a box plot. Say I have two groups here, 1 and 2, and then my y value doesn't matter. And say I had something like this for one box and something like this for my other box. So what I'd be looking at here, these are my y values on a box plot. And I'd be trying to see if the interquartile range is pretty similar there. All right, so I would be looking at this distance from this line to this line, comparing it to the distance between this line and this line. And that's probably the only thing that I would generally do before actually running the model and then checking the rest of the assumptions on the residuals. Now we also have a bonus assumption. Okay, and I'm calling it a bonus assumption because it is not usually listed with the others, but it is important, especially as data becomes more easily available and we just get more and more of it. So the bonus assumption is that there is no multicollinearity in X. All right, no two X variables are strongly correlated. And what would actually happen is, if you have highly correlated X variables, is that they can make the values of beta much larger than they would be if you only had one of the two variables, which will really lead to us incorrectly interpreting the results of the hypothesis test and rejecting a null hypothesis when we shouldn't. And that's almost like the number one sin of quantitative research. So let's talk now about the hypothesis test we are performing with our linear regression. Now that we have our assumptions, we are doing a hypothesis test with linear regression. And hopefully you're at least a little bit familiar with hypothesis testing, because we're not going to go into detail here. But our null hypothesis, we're going to call it H naught. This is our null hypothesis. And we're going to assume that this is true. Okay? Assume this is true. Our null hypothesis is going to be that all of our betas is 0. Right? Beta equals 0 for all I. Now the alternative, which we're going to call H1, is going to be that beta I is not equal to 0 for some I. There exists some I such that beta I is not equal to 0. Now, as you can see, only one of these can possibly be true, and one of these has to be true. All right, and that's how you know if you're doing a good hypothesis for a hypothesis test. Now, we're assuming that the null hypothesis is true. All right, now let's remember that y given x, we said followed a normal distribution with mean beta x and some constant variance. Some constant variance, very important. And we have a finite sample from a normal distribution with an unknown variance. So I'm going to add that here, an unknown constant variance. And so in this case, what we're going to do is we're going to use a t-distribution to approximate a normal distribution. And the reason we're going to use that t-distribution is because it has fat tails. So let's look at this. Let's say right here in blue, this is a normal distribution approximately. Okay, this is our normal distribution. Now, a t-distribution with that same mean and variance is going to have slightly fatter tails like that. And what this does in our hypothesis test is that it puts more, as you can see, more of the probability in the tails here, which is just more conservative or safer. So we're going to use the t-distribution because if the t-distribution gives us a low probability of the of getting our sample given that the null hypothesis is true, then we can really trust that. Now, for our hypothesis test, we need a t-statistic. And the t-statistic is pretty easy to calculate. It's t equals beta I over the standard error. This on the bottom is the standard error of the coefficient. Or it is also the variance of beta I. And we're going to derive that in just a second. We are now deriving the standard error sub I, or the variance of beta I, okay? And we're going to use this. We're going to use that the variance of beta I is equal to n times sigma squared, because remember they're all, the variance is constant, over n times the sum of all the x squareds minus the sum of all the x's squared. This is, again, the standard error, is normally what you'll see it called. But it's actually easier to handle all of the betas at once using vector notation. So we're going to go back to vector notation. And we're going to say that beta, all right, this time beta is the vector of all betas, is equal, as we remember, to x transpose x, the inverse of that times x transpose y. So the variance of that vector of betas is the variance of this whole thing, x transpose x inverse x transpose y, which is actually equal to x transpose x inverse x transpose y times x transpose x inverse x transpose y and transpose of that. So let's distribute this transpose right here, distribute it all the way through. And we're actually going to move, no we're not going to move that to the front. All right, sorry. So here we're going to leave this the same for now, and we're going to distribute this through. So when we distribute this transpose, we have to change the order of the variables. The transpose of x transpose is just x, And here, I'm going to treat this a little bit separately. Transpose. So let's look at this, just this for a moment. So what we can actually do is bring that transpose inside the inverse, and then when we multiply that transpose through, we'll just get x transpose x again. Okay, so after the transpose, we just end up with x transpose x inverse. So at this point, what we have, I'm going to drop these brackets around this front part. We've got x transpose x inverse x transpose y, then this one here, y transpose x, and then this comes over x transpose x inverse. Now this right here, y times y transpose, gives us the variance of y, which we said was just sigma squared. So we've got x transpose x inverse, x transpose, this is sigma squared, this is x, x transpose x inverse. This is a scalar, so we can just move it wherever we want. We'll put it up here on the front. And hopefully you guys are seeing that these two are inverses of each other, so they are going to multiply to become the identity matrix, which we really don't care about. So we're going to leave this as sigma squared times x transpose x inverse. Or if you think about this, this is the variance of y, and this right here is the inverse of the covariance matrix of the independent variables. So we've multiplied that out. It's going to give us, if the x variables are independent from each other, okay? Let's actually talk about that differently. If x variables are uncorrelated, how about that? Are uncorrelated, then x transpose x is a diagonal matrix. So x transpose x inverse is diagonal. And of course, sigma squared times x transpose x inverse is also diagonal. Since it's a diagonal matrix, it's going to look like this. X transpose x. All right, we'll use gamma. Why not? Gamma will be our variance of each beta I. So it's going to be gamma 1 squared, and then zeros everywhere, and zeros this way as well. And then gamma 2 squared, and zeros everywhere, and this way as well. And then gamma 3 squared, and zeros everywhere, this way as well, all the way down to gamma n squared. All right? So the variance of beta I is the ith term from the diagonal of that matrix. And that is where the standard error comes from. So now we have standard error sub I, and we're ready to proceed with our hypothesis test. And our test statistic, again, is t equals beta I over that standard error. And the degrees of freedom for the t statistic is, I'm going to call that df sub t, is going to be n, okay, that's the number of observations, minus k. this is the number of independent variables. And you need both, you need degrees of freedom to work with a t distribution. So once you've found t, once you have t, you can look up significant values, okay, critical values, that's what they're called, critical values, from a t-table. That's how people used to do this back before we had, calculators and computers or everything. Or you can calculate the probability, I'm going to call this the probability of y given h naught, okay? This is the probability of our sample, of something as extreme as our sample. If h naught is true. So you look up that p-value, all right, and you'll compare it to some critical value or some significance value, which we're going to call, well, it's usually called alpha, but I don't want to use that, compared to significance value, which hopefully you have already selected. And typically it's something like 0.05 or 0.01, depending on how specific you want to be. And if your p-value is less than your significance value, then you can say that we have evidence that h naught is untrue. So we reject the null hypothesis. In favor of the alternative hypothesis. All right, so in more general terms, if your p-value is less than the significance value, there is evidence that the alternative hypothesis is true. Nope, I don't like that. There is evidence that supports, there we go, the alternative hypothesis. Or the other way, if your p-value is greater than the significance value, then there is no evidence to support the alternative hypothesis. And there you go. That's basically how you would go about drawing statistical inference from a linear regression hypothesis test. There are a couple of important caveats to this hypothesis test. All right, and these are especially applicable in finance, where we are using time series data for this. But number one, there should be a good theoretical reason for the relationship. to exist. So even if you've run this hypothesis test and you found that your independent variable x had a statistically significant effect on your output variable y, all right, meaning that your p-value was less than your significance value, you still need to have a good theoretical reason why that relationship exists. Otherwise, you may have just found like a phantom relationship, okay, which is really just an artifact of the specific data set, and it'll disappear quickly, and it is not useful. And that actually happens a lot more than you would think. It's one of the major problems in quantitative research. And it becomes a bigger problem the more research that you do. Because our p-value is something like 0.05 and it defines a probability, the probability of getting a observations at least as extreme as the ones that you got, given that your null hypothesis is true, then if you run 100 experiments with the same independent variables, even if you use different data sets, you would expect 5% of those to draw the wrong conclusion. So it is a big problem in quantitative research, and it's a problem that Bayesian experimental methods actually go pretty far toward eliminating, but it's something that the entire research community is still struggling with. So you just need to make sure there is always a good theoretical reason for the relationship to exist. And caveat number 2 is specific to time series regression, which is very common in finance. Observations are not generally independent. Observations are likely not independent. Now, I say time series regression, and in general, when you say that, you're thinking, you're regressing one time series on another, and that is true, but in just any kind of data collection, there is always a sort of time dependency there. I mean, think about anything. We talked about temperature readings earlier. If you take a temperature now and you take a temperature in an hour, even though a good amount of time has gone on and the temperature can change pretty rapidly in an hour, they're still not really independent. Or if you think about if you talk to one student, all right, and get some data from them, and then 2 days later you talk to another student, unless you personally did everything exactly the same, it's really hard to say that there's not some kind of dependency problems there. So this is always something you need to be thinking about, is how can you make your observations more independent? And that's something that good experimental design goes a long way toward helping with. But some ways to fix this. Specifically, there we go, when regressing time series. And I mean time series like stock prices or things like that, things that definitely have this time dimension. One, make sure it is stationary. Make sure time series are stationary before regression. And it's kind of outside the scope of the course, so we're not going to talk about what stationary means. I am planning a time series analysis course, so that will probably be a big part of it because it's a super big deal, stationarity. And next, you need to test residuals for stationarity. So, stationarity. Even though you might have made your time series stationary before doing the regression, there is no guarantee that the residuals won't be stationary. And the other is also true. All right, even if your time series are not stationary before you run the regression, you might still find that you have stationary residuals. So you really need to check on those. And the reason that we do this one is that residuals in spurious regressions. And a spurious regression is, say you have two time series, and they look kind of like this. You have one that goes like this, and you have another one, and it looks kind of, oops, it's supposed to be red, and it looks kind of like this. Now, those both have an upward trend, right? So in a spurious regression, your regression might be finding the trend rather than the actual relationship between the two. So residuals in spurious regression theoretically are not stationary. So non-stationary residuals is a big sign of spurious regression. And of course, even though you do all of this stuff, you have to go back to this one. There should always be a good theoretical reason for the relationship to exist. Now, our model actually contains more information about any significant relationships we might find than the hypothesis can tell us about. And that's where interpreting the coefficients really becomes important. So let's go back to our more finance-looking equation here. Y equals alpha plus beta x plus epsilon. Or, if we expand on this term here, alpha plus beta 1 x1 plus beta 2 x2 plus and so on plus beta n xn plus epsilon. So the rate of change of y with respect to any variable x, okay, the derivative of y with respect to x, is really just going to equal that beta. Or if you think about it in terms of slope, okay, a 1 unit increase in x is going to account for a beta units increase in y. Okay, basically rise over run. And this tells us both the direction and the magnitude, I suppose, of our relationship. So a large positive value for beta, so let's say that beta I is much, much greater than 0, implies that a small increase in x could lead to a very big increase in y. Or let's say beta I is really close to 0. It's small. Then a small increase in x, let's actually say that it is small and negative. All right? So if beta I is small and negative, wrong direction, then a small increase in, a very large increase in x might lead to a small decrease in y. All right, so the direction definitely matters. And when interpreting the coefficients, it's the first thing you want to look at. And so a positive beta implies that an increase in x leads to an increase in y. And a negative beta implies that an increase in x leads to a decrease in y, or a decrease in x leads to an increase in y. So this will tell you which variables x you would want to increase or decrease if you have the power to do so. And the second thing we want to look at is the size of the coefficients, but these really need to be interpreted relative to the size of the target variable and the x variable that the coefficient goes with. So let's say, for example, we're trying to predict S&P 500 returns using GDP. Okay, so I'm going to say this. S&P is related to GDP. This is like the R functional notation, if you guys are familiar in programming with R. So S&P is related to GDP. Now S&P is our Y value, and it is on the order of like 0.01, something like that, very small, whereas our X variable here is on the order of trillions. So of course beta is going to be really, really small, right? Beta is going to be close to 0 no matter what direction it is, because it's got to get from the order of trillions down to the order of 0.01. So even though a very, very small beta, a small increase in X could still make a big change in Y, just because X is so much bigger than Y. And that is one of the reasons why we might scale the variables before regression. All right, it makes size comparisons and some parts of interpretation a little easier. Talking about scaling. And there are many ways to scale variables, but the most common is standardizing, like finding a z-score. And the way you do that is you take each x, and you subtract it from the mean for that x, and you divide by the standard deviation of that x. All right, and that's going to take everything to a normal distribution scaled between zero with mean 0 and standard deviation. There we go, 1. And then if you do that the same for y, then you will get it on the same scale. And that way, when they're scaled like that, you can interpret betas. You can make size comparisons between betas very easily. You can say if beta 1 is bigger than beta 2, then x1 has a bigger impact on y than x2, which you couldn't say before you scaled them. And the direction stays the same. So a larger positive beta would mean that that x variable has a larger positive impact on y. Of course, the issue with this is that you can no longer understand the coefficients as being the slope of the line. All right, so a 1 unit increase in x is not a beta unit increase in y. Not anymore. Okay, we have removed this slope-like interpretation in favor of being able to make size comparisons. But we can compare betas more directly. So those are the things you need to be considering when you decide whether you want to scale your variables or just regress on the original variables. All right, now it's time to actually go in and do some statistical inference with linear regression. I've got a collab open here. As you can see, I've already mounted my Google Drive. And over here, this is the data set we're going to be working with. It's off of Kaggle. And I chose this one because the documentation is great, and I think the problem is interesting. So this data set is about student achievement in a couple of Portuguese schools. And the information that they give us, they've got 2 different schools, either the Gabriel Pereira School or Musino de Silveira. I don't know, not Portuguese. Biological sex, in this case, they're saying is either male or female. You've got age, student's address, it means they're either urban or rural. Their family size, they cut it off, it's either less than or equal to 3 or greater than 3. So if you can think about it, this is kind of saying whether or not they have siblings. All right, parental status, whether they live together or not, mother's education level, father's education level, mother's job, father's job. The reason they chose their school, whether they live with their mother or father or other, how far from the school they live, how much they study during the week, how many classes they failed, whether they get extra educational support at school, family educational support, extra paid classes like tutoring or something like that, I would assume, whether they take part in extracurricular activities, attended nursery school, which I'm thinking is like preschool, whether they plan to go to college, whether or not they have internet at home, if they're in a romantic relationship, how is their family life, how much free time do they have, do they go out with friends, how much do they drink on the weekdays, how much do they drink on the weekends, how healthy are they, and how many times have they missed school so far. And then as target variables down here, or as dependent variables, we've got a first period grade, a second period grade, or a final grade. Now back up at the top, it says, important note, the target attribute G3 has a strong correlation with attributes G2 and G1. This occurs because G3 is the final year grade issued at the third period, while G1 and G2 correspond to the first and second period grades. So I'm not entirely sure how schooling works in Portugal, but it kind of sounds like maybe there are three semesters or something like that, and so we've got a first semester, a second semester, and then a final grade for the whole year. So we're really just going to use G3 as our target variable. But the first thing we need to do is get that data over here, and it's a little complicated to do that from Kaggle. No, it's not. It's real easy. Watch. You need to make a directory that's at the root, and it's called .kaggle, and then you need to bring in your kaggle.json API key, which mine I have saved in my Google Drive. And you need to bring that into the new folder that you just made. And then you're going to want to do this thing chmod 600, and you're doing this to that thing that you just made, Kaggle/Kaggle.json. Let's go into my drive here and see what is going on, because that kaggle.json does too exist. It's right here. See that? What am I doing wrong, I wonder? Whatever, it worked now. Great. Alright, let's go back up and close this. Now, we need to bring that in from Kaggle. We're going to go back to this website and just copy the API command. To run that, you just put this in there, and it's going to bring it in, as you'll see in a second, as a zip file right here, .zip. So we need to unzip it. Unzip student-performance-data-set.zip, and we're going to put that in student-performance-dataset. All right, that should do it. And here it is now. You see we got this folder, and it's got all of our CSV files in there. We're going to use this one, which contains their math scores, because I'm a math guy, and that's what I'm into. But let's go import some libraries. We are going to need pandas. We will bring in NumPy. We're going to want to, plot things, so we'll bring in pyplot and Seaborn. And we want statsmodels.api as SM for actually doing the ordinary least squares regression. I forgot the S. There you go. Done. Alright, let's load our data in. We're just going to call it data, and we're going to use pd.read.csv. It is in student performance dataset /student-math.csv. And let's see what that looks like. Oh yeah, I forgot. The separator isn't a comma. It is a semicolon. You see how there's a semicolon separating everything? So you need this additional sep equals semicolon. And there it is. So you can see we've got 395 observations and all of those variables that we talked about. Let's just make sure that there aren't any missing values. Okay, isNA.sum. That's going to tell us how many missing values are in each column. But if we do sum again, it'll tell us how many missing values altogether, which is 0. Now this is a lot of independent variables, and I don't really want to keep that many. So let's go ahead and just say that our y variable is going to be just the G3 column. And let's only keep, some good ones. Let's decide what we're going to keep. We'll call this keep vars. And let's go look. We'll read over here where it describes them. School might be important because it'll be like we don't want the difference between schools to color our perception of the difference between other things. So we're going to keep that variable in, even though it's not really one that we care about very much. Same thing with sex. We'll keep that one. What else have we got? We've got age. I don't want to use age. Address, urban or rural. Sure, I'll keep that one. Why not? What's next? Family size. I do think that's interesting. Whether or not they have siblings might be important. Living together or apart. Nah. How about mothers and fathers' education? I think that's a good one. Mothers and fathers' jobs. So I'm going to skip reason to attend the school. Skip guardian. Skip travel time. Skip study time. Let's keep that one. Study time, failures, skip. School support, keep. Family support, keep. What else we got here? Family support. Paid tutoring, that's a good one. Let's keep that. Extracurricular activities, skip. Nursery school, skip again. Higher education, skip. Internet access at home, we will keep. But when we're thinking about the effect that internet access at home might have on a student, we really have to consider that having internet access at home probably is very strongly correlated with maybe what the parents do or how educated they are, but really it's about how much money they have. So we're keeping internet access at home, but any conclusions we draw about internet access, since we don't have like household income as a variable, we're not going to be able to separate the impact of income and internet. We're just not going to be able to separate those two. All right, what have we got? Romantic relationships. I'm going to keep that one because I think that one's interesting, whether or not they're in a romantic relationship and how that affects their schools. I want to keep free time and how often they go out as well. Just down on a third level. But the rest of these, how often they drink, I don't want to keep that. I think that's a weird one. And their health status, number of absences, I'm not going to keep those. And again, our only target that we're actually going to care about for this is their final G3 score. So we've got all of the variables that we want to keep. How many of those do you think there are? Let's find out. It's 14. All right, so we're going to keep 14 independent variables, and we have one dependent variable. Okay, there we go. It's 395, and there's 14 of them. All right, we're going to go ahead and explore variables now. We're just going to start by looking at a description. Well, actually what we're going to do is we're going to go up here and look at these D types. All right, they're mostly objects, which means words, or integers. And if we go over here and look at the descriptions, then we can see that mostly they're either binary outcomes or they're 0, 1, 2, 3, 4, 5 outcomes. So this describe actually isn't going to do anything for us. How about value counts? Let's see what we can get from this. There's way too many of these. Forget that. All right. So in the school column, we can see that 349 of them went to GP and only 46 went to MS. What's next? We had sex. 208 females, 187 males. What other columns do we have again? Address, that's a good one I'd like to look at. (307) urban and 88 rural students. It's interesting. You know what? Why don't we write, how many is there? There's 14. So why don't we go ahead, and what we're going to do is we're actually going to write a loop that goes through and makes just a bar plot, all right, of the different value counts for these. I'm going to speed this up because this might take a minute. There we go. So now we can see all these bar plots. You can see school, it's either GP or MS. There's like 350 GP and a little less than 50 MS. Sex, about 200. Females, 180 or so. Males, 75 or something. Rural students, 300 or so. Urban students, everything like that. Most of them had family size greater than 3. Most people did not get extra school support. This is, how much study time they have. Father's education level, pretty centered. Mother's education level, a lot of the mothers had a pretty high education level. Let's go back and see what 4 means. It means that the mother went to college. 2 means the father quit school between 5th and 9th grade. As you can see, there's quite a bit of that here. Study time being a 2. Down here means they study between 2 and 5 hours throughout the week. Now, family support, most of them had that. Extra paid support, it's pretty close to 50-50, which I'm surprised by. Almost everybody, or at least most of them, had internet at home. About 2/3 or so are in romantic relationships. Here, this free time, let's check what that is. Free time and go out, both of them were about in the middle. So let's see what that means. Free time after school, 3 means they have some, but not a whole lot. I guess, how often do they go out? Sometimes, but not all the time. Now the next thing that I want to do is I want to get all of these variables that are binary. So let's make a list of those. Let's see, there's school, there was sex, what else is there? Address. Let's scroll up a bit and see what we've got. Fam size. And what we're going to do once we've got these is we're going to look at box plots. Split up by this. School support. Fam support. Paid support. What else we got? Fam support, paid support, internet at home, and romantic relationships. X binary is going to be X, just those variables. Go ahead and make sure that this is good. Alright, looks nice. Now we're going to write that same sort of thing again. How many of those do we have, by the way? Alright, you can see here, school, between the two of them, it's not that different. Sex, between the two of them, it doesn't look that different either. Address, what we're really looking for here is signs that the variance is significantly different, is like very different between the two groups. So really we're saying, is the distance at least between these two, between like the height of the box itself, is that super different between the two groups? And so far, this one might be the one that I'm seeing the most difference in, but none of them are so bad that it makes me really nervous right off the bat, and that's great. We can also right now look at KDE plots of the other ones, but looking at them right now, I'm okay with this. I don't want to worry about these other independent variables anymore. All I really want to do is check for correlation between independent variables. And the way we're going to do that is pretty easy. We have our x already. You can see what this spits out. And look at this. Mother's and father's education is actually pretty highly correlated. Okay, can only check correlation between the numeric variables. So it can't check for that in between these binary ones. Which, actually, maybe we should go ahead and make dummy variables first. Let's do that instead. So to make our dummy variables, what we're really doing is one-hot encoding, and we're going to use this, pandas.getDummies. Okay. And when we do this, we want to do drop first equals true. Because when you drop the first one, what this is going to do is it's going to change all of our binary variables to zeros and ones. Okay, if you set drop first equals true, then you're going to get, for a single binary column, you're going to get one column of zeros and ones. Whereas if you set it to false, then you're going to get two columns of zeros and ones. Where if you're, say for sex, then what we want is a single column where 0 refers to either male or female and 1 refers to the other. Whereas if we set drop first to false, which is the default, then we're going to get a female column that has 1s for females and 0s otherwise, and a male column which has 1s for males and 0s otherwise. So we're going to get two columns that actually has exactly the same information in them. So we're definitely going to use this drop first equals true. So xDummy is going to be pd.getDummies, and we're going to feed in xBinary, and we're going to do drop first equals true. And see what we get here? School MS. Alright, so this means it's a 1 if the school is MS. Sex, M. So this, a 1 means male. So these are all females who went to GP. Address U, it's a 1 for urban. These are urban females who went to GP. Family less than or equal to 3. 1 means less than or equal to 3, so this one has siblings, is urban, is a female, and went to GP. See how this goes? Alright, did they get school support? Did they get family support? Did they get paid tutoring? Do they have internet at home? Are they in romantic relationships? And down here, what I'm doing is I'm just checking the D types, U and 8. Perfect. Okay. So, what I want to do here is I want to replace all of the columns in X that are also in X binary. I want to replace those columns with that binary, with the dummies column, right? So now you can see I've replaced school, sex, address, blah, blah, blah. All right, with that, I also want to change the actual column names. that didn't work. Oh well. That's fine. So school is now zeros and ones, sex is zeros and ones, address ones, blah, blah, blah. These ones that we did not dummy encode are still 1, 2, 3, 4, and so on. But that's all good. Everything is now an integer, and we can check the correlation. So we're going to call this the correlation matrix. And let's just look at it real quick and see all these correlations. But a much easier way generally to do it is in a heat map. I think 20 by 8 looks nice. I don't know why. Format, let's see. I want the center to be 0. And what else do I want? Anything else nice? CMap. I like yellow, green, blue. I think it looks good. Let's get rid of the center equals 0 and see what that looks like. This is pretty iterative. So as you can see down the middle, everything is very highly correlated with itself. But then outside of the middle, really what is correlated is having free time and going out with friends. Appears to be, you know, somewhere in this area, maybe 0.3, which isn't a big deal. Or the fathers and mothers' education levels look to be pretty highly correlated. And we're not going to worry about that so much here, but that is something that you might think about if you're doing this research and trying to get it published. You might just consider having like maybe a parental average or similar, rather than keeping them as two separate variables. It'll really be up to how you want to talk about it and what you really want to be able to say. So I'm not seeing anything right now that strikes me as so much correlation that we need to get rid of a variable or anything. So we're just going to go down here and we're going to actually run the regression. Now there's a great tutorial on the stats models documentation about how to do this. Alright, we've already got stats models at API. And if we walk through this real quick, this sm.add constant, what that does is it adds a column of all ones, all right, so that we can have an intercept, okay? And then down here you call OLS with y and x, and then you fit it. And so that's what we're going to do. Okay, x equals sm.add constant x, and then we're going to call this the model, and that is going to be sm.ols with y in it and also x, and then we're going to say that results is equal to model.fit. Go ahead and run that. Everything looks fine. It's giving me some kind of warning about the future. Doesn't matter. And we're going to print the results.summary. And look at our table. Look at this thing. Now, our adjusted R-squared is not very high, so you probably wouldn't want to use this model for prediction, and that's fine. That's not what we're interested in. What we're really interested in mostly here are these p-values, this column. All right. So this here, the constant, the intercept, very important. Can't get rid of the intercept. Which school they went to really did not matter, which I think is very interesting. Now, sex itself, male versus female, has a p-value of 0.08. So most often, people will say that, oh, you know, it's statistically significant if the p-value is less than like 0.05. But that's kind of arbitrary. It's kind of nonsense to think about it that way. Just know that this is low enough that it kind of looks like there might be a relationship, all right, between being male or being female and a person's score, all right, a person's final grade. Now here, a little less evidence that urban versus rural matters. You know, decent evidence about people having siblings either doing better or worse. Mother's education level seems to matter quite a bit, but father's education level not so much. And remember, those are pretty highly correlated. So
there definitely could be some kind of relationship between them that is messing this up. It could just be that, like I said earlier, average parental education is important. We don't know. But it looks like study time is pretty important, which makes sense, doesn't it? The more you study, hopefully, the better you do. Whether or not they got extra school support doesn't look like it's very important. But family support does look pretty important. Isn't that interesting? See, it looks from here like people who get help at home are better off than people who get help at school. Paid tutoring is kind of important, I guess. Internet didn't matter, which I think is interesting because, like we said earlier, internet probably correlates pretty strongly with their household income, and you would think maybe household income would be important, but it looks like that might not be the case. Although I also bet that internet and parental education were somewhat correlated. Let's go up here and find out. Where's internet and mother's education, father's education right there? They're a little more correlated than most. Now it looks like romantic relationship was pretty darn important. And if we look over here real quick, it looks like having a romantic relationship is bad for your schooling. Okay. And then free time didn't matter so much, but going out a lot apparently did. Where is that? Here. Those are pretty kind of correlated too, free time and going out. But see, it looks like going out makes a big difference. Probably the biggest difference of all of them. Very interesting. As we can see here, our skew, you really want this to be close to 0. It's an indicator of normality of residuals. This is, you know what, skew of negative 0.8. It's not great, it's not horrible. Kurtosis, you want this to be close to 3. 3.5 is also not great, not horrible. We're going to do more to look at the normality of the residuals, actually, in just a second. So we're examining residuals, and we can get these pretty easily by going to results.resid. See the residuals show up like that. Well, let's go ahead and save them. Res equals this. And we're going to plot them. All right, we're going to use sns.scatterplot. X is going to be the residuals index, and Y is just going to be the residuals. And what we want is for them to be centered around 0 and for them to be about the same distance from 0 the whole time. But that's not what we're getting. You see that they're somewhat centered around 0, except that there's all of these down here, where there's not over there, but it is down here. And that's a pretty clear sign that we've got some kind of variance problem that our model is not capturing. And so the results from our model are maybe not as trustworthy as we might have hoped. There's a couple more ways that I think we ought to look at them. And what we're going to do is we're going to put the original y values, the target variable, on the x-axis, and we're going to put the residuals on the y-axis. And what we would want here is, again, for them to be in kind of a straight line, but we see that there is a relationship between the G3 score and the residuals. All right, the higher the score is, the higher the residuals tend to be, or possibly the lower. All right, and that in itself is also a problem. The last one that we want to look at is we want to get the predictions from the model, and we want to do a scatter plot where the predictions are on the x-axis and the residuals are on the y-axis. So let's look at that here. And as you can see there, we want these to be flat again, but they are not. We can see there is a negative relationship where the higher the predicted score, the lower the residual is. And none of those are very good signs. But there are a couple of other things that we can look at. First, let's go ahead and let's explore a little bit about the normality of the data. So to examine the normality of the data down here, we can do a dist plot from Seaborn. Let's see what that looks like. You know what? It's actually not so bad. It's got this little hump down here. But that's not awful. I've definitely seen worse. But let's try a QQ plot. Let's see if I can remember how to make a QQ plot first.
So I'm pretty sure that it is stats models dot graphics dot let's see. Is this it? That ain't it. How about this? There we go. We're changing the location and the scale to put both the x and y axes on the same location and scale. It makes it more interpretable here. And you know what? I actually think I want a line. 45-degree line. Let's try that. And look, this is actually not terrible. All right. If you use what's called the fat pencil test and you imagine yourself putting a fat pencil down on that line, would it cover all the dots? And honestly, it would get very close to covering all of the dots. So the non-normality of the residuals doesn't appear to be that big of a problem. The bigger problem really is this relationship, this leftover relationship, that is something that we're not capturing. But you know what? For our purposes, we're actually going to say that this is fine, and our last step is to just interpret the results totally. And what did we see? Well, we saw that going out with your friends was significant, and it has a negative effect on your final score. People who spend more time with their friends have lower scores. Personally, I was hoping that it would be the other direction, because, you know, who wouldn't rather go out with their friends than study all the time? But going out with your friends was negative, whereas study time had a positive effect on your final score. And it actually studying had a smaller positive effect than going out had a negative effect. Isn't that interesting? And look at this one. Family support was important, but family support has a negative effect also. So it seems like people who got help from their family, there's really two options here. Either their family was teaching them badly, or they were getting help from their family because they were struggling. And you know what? Even though this one ended up having kind of a high p-value, the fact that school support has a negative coefficient makes me think that getting more support has lower grades because the people that are getting additional support are the people who are already struggling. And so this one, getting paid support, they had a positive value. And I think that might be the case because a family that's going to pay an extra tutor to come help their child probably already puts a lot of work into helping their child in school. So these are probably being given to students that are already getting a lot of support and probably aren't struggling as much. Last one I really want to talk about is this. Being in a romantic relationship had a big effect, didn't it? It had the largest effect out of all of the independent variables that we tried. And it was very negative. People that are in romantic relationships, man, do they do worse in school. And that one, I think that probably is the relationship. If you're in a relationship, you're probably spending too much time with your significant other, not enough time on your studies. And I bet that actually is what's happening. Whereas all of these other ones, the different kinds of support and things like that we talked about, even though what we're seeing is the negative relationship between additional educational support at school and final grade, that's not the cause of the lower grade. All right, getting more support in school probably isn't causing kids to do worse, but kids that are already struggling are the ones that are getting the support. Whereas for romantic relationships, the relationships probably are the reason why the kids are doing worse in school. And that's it. That's inference. We went through everything. We brought in the data. We explored it a little bit. We checked it out before modeling. We got our dummy variables. We looked at correlations. We ran the model. We checked the residuals down here. We found that our model was not great, but we interpreted the results anyway. After ordinary least squares, which is what we used when we wanted to draw inference, the second most popular way of fitting a linear regression is by maximum likelihood estimation. And kind of as the name implies, we're trying to find the values of beta that maximize the likelihood of the observations. So we want beta such that it maximizes the probability of y given x and beta. Now, because y values are independent, we can say that the probability of y given x and beta is actually equal to the product from I equals 1 to n of the product of y, the probability of y sub I given x sub I and beta. Now, the best thing about this is that we can use any distribution here. So in OLS, we were assuming that it was a normal distribution. But here we can use any distribution. And what you'll see a lot is the assumption that it is a Poisson distribution. Poisson regression is very popular, right? And it works in a lot of ways. But right now, we're going to keep the assumption that it follows a normal distribution. And you'll see why we're looking at that case in just a little bit. So we're going to say that the probability of y sub I given x sub I and beta follows a normal distribution with mean x sub I beta and variance sigma squared. And what this looks like is 1 over sigma times the square root of 2 pi e to the negative y sub I minus x sub I beta squared over 2 sigma. All right, that's what our normal distribution looks like. So every single one of these follows this function. So our probability altogether then of all the y's given all the x's and beta is going to be the product from I equals 1 to n of 1 over sigma square root of 2 pi e to the negative y sub I minus x sub I beta squared over 2 sigma. Now what makes this hard, okay, we want to maximize this. And what we'd like to do in order to find a maximum is to use the first derivative. But what makes it hard is this product right here. But what we can do in order to deal with the product is to take the natural log of both sides. So we'll do the natural log of the probability of y given x and beta is equal to the natural log of this product from I to n square root of 2 pi times e to the negative y sub I minus x sub I beta squared over 2 sigma. And if you think back to college algebra or pre-calculus or whatever class you took, the rules of natural log say that the natural log of a product, natural log of, say, a times b, is equal to the natural log of a plus the natural log of b. So we're going to use this idea to make this product turn into a sum. So down here, instead of the product, we're going to have the sum from I equals 1 to n of the natural log of this stuff that's inside. Sigma square root of 2 pi times e to the negative y sub I minus x sub I beta squared over 2 sigma. Now we have another product in there, so we can break that apart further. The sum from I equals 1 to n of the natural log of 1 over sigma square root of 2 pi plus natural log of e to the negative y sub I minus x sub I beta squared over 2 sigma. And all of this stuff is happening inside that sum. Now the natural log and this e cancel each other out. So let's keep going here. 1 to n natural log of 1 over sigma square root of 2 pi plus negative y sub I minus x sub I beta squared over 2 sigma. Now what I want to do is I want to distribute the sum, but I also want to bring this out, okay? So we have now the sum from I equals 1 to n of the natural log of 1 over sigma square root of 2 pi minus the sum from I equals 1 to n of y sub I minus x sub I beta squared over 2 sigma. Now this doesn't depend on I. So it's really just going to end up being n times the natural log of 1 over sigma times the square root of 2 pi. And this is all equal to, remember, the natural log of the probability of y given x and beta. Now this we can work with in the first derivative. Back when we had a product, we'd have had to use the product rule like however many times, and that would have gotten really complicated, but we don't have to do that now because everything is a sum. So now we want to take the derivative with respect to beta of both sides here, in natural log 1 over sigma square root of 2 pi minus this sum from I equals 1 to n of y sub I minus x sub I beta squared over 2 sigma. So we really only care about this half. And let's look at this piece. This piece has no betas in it. So really that is just going to end up being a 0. So we're going to get 0 minus the derivative of the sum from I equals 1 to n of y sub I minus x sub I beta squared over 2 sigma. I went ahead and moved the negative out. Now we can also move this out front. Let's go ahead and do that. Get rid of the 0. We don't care about it anymore. 1 over 2 sigma. Remember we moved that out front. Times the derivative with respect to beta of the sum from I equals 1 to n of y sub I minus x sub I beta squared. I'm going to write that a little bit different down here. We were taking the derivative with respect to beta of this. Now if you think back to when we were talking about OLS, this is actually equal to y minus x beta when they are vectors, and this is a matrix, times, sorry, this is transpose, y minus x beta So what we've got here is negative 1 over 2 sigma, the derivative with respect to beta of y minus x beta, I'm dropping the vector notation transpose, times y minus x beta. And when we take the derivative there, negative 1 over 2 sigma, and we'll take this derivative, and we would end up, once again, with negative 2 x transpose times y minus x beta. And because we're doing the first derivative test, we can set that equal to 0. And you can see that all of these constants at front don't really matter. We can just divide by all of them, and they go away. And we have x transpose times y minus x beta is equal to 0. And we can solve for that just like we did before. Get x transpose times y minus x transpose times x times beta is equal to 0. Or x transpose times x beta is equal to x transpose times y. Or beta is equal to x transpose times x inverse times x transpose times y. And this is exactly the same result as OLS. And that's why we did the assumption of normality. If you assume that y given x and beta is a normal distribution with mean x beta and some constant variance sigma, then you get exactly the same result for beta, whether you are using OLS or maximum likelihood estimation. But I mean, the best thing about maximum likelihood estimation is that it doesn't have to be normal. You could say that y values are log normal, or as in logistic regression. Or you could say that they follow a Bernoulli distribution, or that's binomial, or whatever distribution you like. But this is the idea. No matter what distribution you use for the probability of y given x and beta, no matter what distribution you use, you will do the same thing. You will start off with the product of the independent y distributions. You take the natural log of both sides, and then you use a derivative in order to find the value of beta that maximizes that probability. Our third method of finding beta for a linear regression is called gradient descent. Gradient descent. And it's very common in machine learning. There's also something called stochastic gradient descent, which we will talk about a bit more in just a little bit, is used for almost every kind of model imaginable. Now, I'm talking random forests, neural networks, XGBoost, everything in between. Stochastic gradient descent or just plain gradient descent are very common in machine learning. So in OLS, or in maximum likelihood estimation, we took the first derivative and optimized the function. But when we can't or don't want to take the derivative, we can numerically approximate the derivative and use that. Okay, so that's the idea, is that we're going to numerically approximate the derivative, okay, and use that. And so methods of numerically approximating the derivatives are pretty well outside the scope of this course, but if you look at the function, okay, the definition of a derivative, that's the limit as h approaches 0 of f of x plus h minus f of x over h. You can probably figure out a method or two of approximating a derivative. But let's go ahead and try a gradient descent of our own. So let's pretend we're going to use a very small table of values because we are doing this by hand. All right, we're going to have x is 0, 1, and 2, and we're going to have y is 0.1, y is 2.1, and y is 3.9. Now, if you look at those, you might be able to guess that y is something like 2x plus epsilon. That's my guess. I don't know, just based on looking at it. But we're going to check. So what we need for gradient descent is a loss function. And that's what we're going to try to, that's what we're going to use in order to, optimize this. So our loss function is going to be the mean squared error, which is y minus beta x squared. And that's the same thing as OLS. OLS also optimizes this loss function. And when our maximum likelihood estimation assumed a normal distribution, we were also optimizing this loss function. So you can really see how all of these things are connected. Now, we also want the gradient of the loss function. And the gradient in this case is the derivative with respect to beta. But really, the gradient is it's a measure of how the loss function changes when the coefficients change. Which ours is negative 2x. I'm just going to leave it as singular, and you'll see why in a minute. Negative 2x times y minus beta x. So now we're just going to guess what beta is. So let's say let beta equal 1. All right, seems like a pretty good guess. Then let's see what our gradient is. Okay, so what we're going to do is we're going to plug in values from here for our gradient. So we have negative 2 times 0 times y, which is 0.1 over there, 0.1 minus beta, which is 1, times x, which is 0, squared. And if we multiply that all out, it's going to end up being 0. And we'll have negative 2 times 1 times 2.1 minus 1 times 1, which is 1, squared. And let's see, we multiply that all out. Do you have your calculator on you? I gotta get one. 2.1 minus 1 is 1.1. Square that, multiply by negative 2. How did I mess that up? Okay, times negative 2. And we'll get negative 2.42. One more, negative 2 times 2. Here we have 3.9 minus 1 times 2 squared. Calculator again, 3.9 minus 2 is 1.9. Square that. Multiply by 2, then multiply by negative 2 and to get negative 14.44. And we're going to find the mean of this, so add those up and divide by 3. And the mean gradient is, let's see, negative 2.42 minus 14.44. Divide that by 3, negative 5.62. Now we're operating under the assumption that the loss function here looks like this, right? Which is true because look at this squared. It looks something like this. So the gradient here should look something like this. And what we've got is negative 5, which tells us that we're somewhere over here. And what we want to be is right there where it crosses 0. So what we need to do, this is our beta axis, we need to move beta up. Okay, so this is negative, tells us to move beta up. So let's try beta equals 2. And then we got to find our gradient again. So we have negative 2 times 0 times y is 0.1 minus x is, 0. And beta is 2 squared. Multiply all that out, we are still going to get 0. Next, when x is 1, y was 2.1. X is 1 and beta is 2. Square that. And let's see what happens. We have 2.1 minus 2. 0.1 times square that times negative 2. We have negative 0.02 here. And then negative 2 and 2. And this was 3.9 minus x is 2 and y is 2 squared. 3.9 minus 4. Go ahead and square that to get positive 0.01 times 2 and then times negative 2 to get negative 0.04. And let's find the mean gradient here. Negative 0.02 minus 0.04. Divide that by 3 to get negative 0.02. Now this is close to 0. Close to 0, which tells us that beta equals 2 is close to optimal. And that's the general idea behind gradient descent, is you kind of guess. You hopefully an educated guess at what beta might be, and you go ahead and calculate the gradient. You take the mean gradient, and that tells you whether you need to move beta up or down. And you keep going until your gradient is close enough to 0 that you're happy. You think beta is close enough to optimal that changing it is more trouble than it's worth. And as you can see, it just worked for us. In our gradient descent example, we had to calculate the gradient for every observation and then take the average. But in a lot of machine learning, projects, we might have thousands or maybe even millions of observations. So doing all those calculations can be like super slow. So with stochastic gradient descent, we randomly pick a subset of observations if it's a batch gradient descent, or sometimes even just one single observation, and calculate the gradient for that and just use that as our gradient. Now, SGD, stochastic gradient descent, it can take a lot longer to converge, but the time saved by cutting the number of calculations from each iteration makes it much faster than gradient descent with similar results. The weak point of linear regression is relatively poor out-of-sample predictive performance. Now, linear regression has high variance, which means that relatively small changes in the data can have a big impact on the model itself, and the model just isn't prepared to handle data that it hasn't seen before. Now, this is always a problem with linear regression, but it's really easy to see whenever the independent variables are highly correlated. So let's take a quick look at how high correlation can cause this problem. So let's say that we have two independent variables that are perfectly correlated. We're going to call them x1 and x2, and the relationship is going to be that x1 is equal to x2 plus some constant here, which we're going to call phi. All right, perfectly correlated. And we've got some regression here. This is our regression. That looks like y equals alpha plus beta 1 times x1 plus beta 2 times x2 plus the error epsilon. Now, I'm no longer going to talk about epsilon. We're going to start writing y hat. And we know that x1 is equal to x2 plus phi. So really what we have here is alpha plus beta 1 times x2 plus phi plus beta 2 times x2. And again, I'm no longer writing this because I'm putting the hat on the y. Now if we multiply this through, we've got y hat is equal to alpha plus beta 1 x2 plus beta 1 times phi plus beta 2 times x2. Go ahead and rearrange things a little bit. We'll get alpha plus beta 1 times phi plus beta 1 plus beta 2 times x2. And this now is a function of one variable of one independent variable. And what's more, this is all a constant, right? So we can just let alpha absorb that beta 1 times phi, and that's going to become our new y-intercept. There we go, our new intercept. So what we really have is y hat equals alpha plus beta 1 plus beta 2 x2. Now if you think about this, for all real numbers, okay, these are all constants, beta 1 equals some k times beta 2. All right, for some k. So if we look at that, we can factor this some more. Sorry, we can replace beta 1 with k times beta 2. And then if we factor out beta 2, we end up with y hat equals alpha plus k plus 1 times beta 2 times x2. Now our whole coefficient for x2 then is this whole entire k plus 1 times beta 2. That's our coefficient for x2. Now as long as that coefficient doesn't change, it doesn't really matter what beta 2 and k are. So for example, if our coefficient is 2, then k could be 0, and beta 2 could be 2, all right, and that would give us 2. Or k could be negative 3, and beta 2 could be negative 1. Or, let's see, beta 2 could be 1,000,000, and k could be whatever k scales to turn 1,000,000 into 2. All right, so as long as this 2, or the coefficient part, doesn't change, it really doesn't matter what k and beta 2 are as long as they multiply together. This whole thing works out being equal to this coefficient. So you can really see that beta 2 is no longer bound to anything. It can become whatever it wants to be as long as beta 1 over here is appropriately scaled to it.
So when the inputs are highly correlated, the model is going to have more degrees of freedom. Instead of being a function of two variables, it becomes a function of one variable, and so it ends up with a lot more freedom than expected. And so it's going to over-adapt to the features. And in machine learning circles, this over-adaptation is referred to as overfitting. And like we saw before, if k is just properly scaled, we could get a huge value for beta 2 and come out with exactly the same predictions. So since the predictions are exactly the same, as far as training the model is concerned, we fit exactly the same model. But now this is in the case of perfect correlation is what we just saw. But what this huge value for beta 2 or tiny value for k, whatever it may be, what this is going to do is it's going to amplify the error when x1 and x2 vary even slightly from perfect correlation. Now from this example that we just saw, it's clearly in our best interest to keep the beta values small. And we can encourage a machine learning model to keep coefficients small by adding a penalty to the loss function as long as that penalty grows with the coefficients. And that's what we're going to look at in this next section on shrinkage or regularization.
In linear regression earlier, we had a loss function that was the sum of squared errors. Okay. Now we talked about RMSE usually, but whenever we minimize the root mean squared error, what we're really minimizing is still the sum of squared errors. And let's just go show that real quick. So the root mean squared error, we had the square root of the mean. So the mean. So I'm going to do 1 over n. Squared error. So we're going to add up all of the errors, square them, divide by n, and take the square root. All right, there's the root mean squared error. Now when we minimize this, like we saw before, okay, the square root goes away, the mean goes away, and we end up with just the sum of squared errors. That's the sum I equals 1 to n of the squared errors. Okay. So from that loss function, we're going to change to first an arbitrary regularized loss function. With an arbitrary regularization function, our loss is actually going to be the sum of squared errors plus some function of beta. This is the regularization function. And it grows with beta values. So what this looks like so far is the sum from I equals 1 to n of the error here squared, okay, plus some function of beta, where beta is the matrix of all of the coefficients that we've found. And this function here, it can be anything that grows as while beta values grow. But there are 3 famous ones. Okay? 3 famous regularization functions. First, most famous is called Ridge, which is spelled G-E if you were wondering. Ridge, okay? And that says that the regularization function here is equal to the 2 norm, or the sum of all the betas squared. Well, that's not the norm, I guess. The norm squared. So it's the sum from I equals 1 to n of all of the betas squared. Let's call this an m instead of an n there. So altogether for this is the ridge regression loss function. It is the sum from I equals 1 to n, okay, of the errors squared, plus the sum from j equals 1 to m of the betas squared. Now it's important that beta naught, or alpha, or the intercept, is not in the penalty. Alright, this allows the penalty to adapt much more easily to whatever, the size of your data, whatever your observations are. If your observations are in the thousands, then you need an alpha or intercept in the thousands, so you don't want to keep that one small. Or actually, in general use, if we change this to matrix notation, what we're actually using is y minus x beta transpose times y minus x beta plus lambda here, beta transpose times beta. Now this is, of course, this is the sum from j equals 1 to m of all of the betas squared. But this guy right here, this is going to allow us to control the amount of regularization. So as you can see, this always grows with beta, but this lambda parameter here, this lambda hyperparameter, the higher it is, the harder this loss function is going to push betas down. Right? So a small lambda will allow betas to grow bigger before they become, the largest part of the loss function, whereas a large beta is going to make sure that lambda is going to make sure that all of the betas remain very small. And one of the best things about ridge regression, why it's used so often, is that if you were to plot this, you'd end up with it being quadratic. All right, it's smooth. The penalty decreases quickly when beta is small, and it increases quickly when beta is large. Okay, so this is the penalty on the y-axis, and this is beta on the x-axis. All right, so if beta is small, we're not getting much of a penalty at all. But if beta is big over here, then we're getting a whole lot of penalty. And this is considered more of a gentle regularization, especially when compared to the second one we're going to look at, which is called lasso. And in lasso regression, the penalty function here, p of beta, is actually equal to the absolute value of beta, okay, or the sum from j equals 1 to m of the absolute value of all of the betas. So our total loss function here, this is lasso regression loss function, is going to be the sum from I equals 1 to n of all of the errors, plus, again we're using lambda, okay, times the sum from j equals 1 to m of all of the betas. And this serves the same purpose as before. It controls the amount of regularization, and higher lambdas means more regularization. In matrix notation here, we've got y minus x beta transpose times y minus x beta plus lambda, and this is just the absolute value of beta there. And if you were to plot this penalty function out, it's the absolute value, so it looks like this. All right, this is the penalty on the x value, and this is beta. penalties on the y, betas on the x, and you can see that the penalty is evenly applied, okay, everywhere. It doesn't have that kind of gentle tapering off that ridge regression had. And so lasso regression is more likely to push coefficients all the way to 0. So a common use of lasso regression is actually for feature selection. So lasso regression can be used for feature selection because it will push small betas all the way to 0, no problem. So say you have many factors, but you aren't sure which are like generating mostly signal and which are generating mostly noise. An OLS regression, it'll fit to the noise and signal equally, which leads to overfitting. But if the signal is stronger than noise, then lasso regression, it ought to reduce the noise coefficients, hopefully all the way to 0, while keeping the signal coefficients. So if there are more features than observations, lasso is actually going to select in best features. So if m, the number of features, is greater than n, the number of observations, then lasso regression will select the n best, I'm putting best in quotes here, features. Which is very cool. Whoa. Sorry, dropped something. Which is very cool, but often it doesn't actually come up that much in practice. Now the third one, and the most complicated, is called elastic net. And elastic net regression, it seeks to form a combination of ridge and lasso. So this penalty function, p of beta, is going to be 1 minus alpha over 2 times the sum from j equals 1 to m of beta j squared, plus alpha times the sum from k equals 1 to m of the absolute value of beta k. Alright, so this is like ridge, and this is like lasso. And so elastic net here is trying to find like a balance between the two. I've used alpha, but I don't like that because we're using alpha for something more specific in this course. Let's change this to lambda. So what lambda actually does is it doesn't just control the amount of regularization here, it's actually the mixing parameter. So let's look at the whole total loss here for elastic net regression. And this whole loss altogether is going to be y minus x times beta transpose times y minus x times beta plus, well, I already used lambda. We're going to use lambda here again. All right, lambda 1 minus, let's use delta. Sorry, we're switching so much. I'm going to replace these with deltas. 1 minus delta over 2 down here times this plus delta, right? Okay, so this is the lasso component. This is the ridge component. And this is the sum of squared errors. Now what this delta, this mixing parameter, really allows us to do is control how harsh, okay, the regularization is. So if delta is equal to 0, then we're actually going to end up with, ridge regression, okay? And if delta equals, say, 1, then we're going to end up with lasso regression. And if delta is, 0.5, then we're going to end up with a slightly softened absolute value function. Importantly, there is a closed form solution for ridge regression. The other ones, lasso and elastic net, don't have a closed form solution. You've got to use some kind of gradient descent, but there is a closed form solution for ridge regression. So let's look at our loss function here, which we said was y minus x beta transpose times y minus x beta plus lambda beta transpose times beta. Okay, and we want to minimize this, so we are going to take the derivative with respect to beta. And when we take that derivative, what we're going to end up with is negative 2x transpose times y minus x times beta plus 2 times lambda times beta. And we're going to set that equal to 0 because we're trying to minimize it. If we go ahead and kind of, solve this, divide by 2 probably, then what have we got here? We've got lambda times beta minus x transpose times y minus x beta is equal to 0, or lambda times beta minus x transpose times y plus x transpose times x times beta is equal to 0. So we can kind of pair these things up. Lambda plus x transpose times x, sorry, forgot the beta there. Beta is equal to x transpose times y. Now we want to factor the beta out, but y, this lambda here is a scalar, so when we factor it out, we're going to get lambda times I, where I is the identity matrix, which of course looks like ones on the diagonals and zeros everywhere else. Okay, so we have lambda times I plus x transpose times x, beta is equal to x transpose y. And when we multiply on the left, over here, by the inverse of this whole thing, then we end up with beta equals lambda I plus x transpose x, all of that inverse x transpose y. And that is our closed form solution for the beta, the coefficients that minimize the loss function for ridge regression. There's an important theoretical aspect to this, which is adding this lambda times I, okay, this diagonal matrix, to the x transpose x ensures that the matrix is always non-singular, even if x transpose x doesn't have full rank. Now that's, like I said, a little theoretical, but what it means is that this matrix of beta values, or vector of beta values, always exists. So this will always work. Alright, we're actually almost done with the course. What we're going to do here, we're going to go through this Colab notebook together. And what we're going to do is we're going to try 5 different kinds of linear regression. And then we're going to, tune their hyperparameters and then compare the performance of each model on completely unseen data. And we're going to try ordinary least squares using the linear regression class from scikit-learn. Then we'll do stochastic gradient descent, which is HSGD regressor. We'll do a ridge regression, a lasso regression, and an elastic net. Now this is in Colab. I've already mounted my Google Drive, and I've got the path to my prepped data. And we're using the same data as before in this other notebook. So just down here, after I had cleaned everything, I don't want to do that again, so I just exported it as a CSV right here. And we're going to be able to load that in just a minute. So let's talk about what we're going to need to import. We are going to want NumPy. We'll want pandas to help us load the model. We're going to need all those things we talked about from scikit-learn. So So let's do from sklearn.linear model import. Let's see, what did we need? We wanted linear regression. We wanted SGD regressor. We wanted ridge. Was ridge the next one? Yeah, it is ridge. We want ridge. We want lasso, and we want elastic net. We're also going to need over here grid search CV and train test split. From sklearn.model selection, import train test split and grid search CV. What else do you think we might want? Maybe let's go ahead and bring in matplotlib in case we want to make some plots later. And in the same vein, we'll import Seaborn. And that should be everything. So what we're going to do next is load the data. And we're just going to read CSV. I've already made this data path right there. Let's just look at the head of that. Now it's brought in this column. You know, there's a setting in this function where you can get rid of that, but it's not a big deal. We're just going to drop unnamed 0, axis is 1, and in place is true. And then let's look at the head again. There you go. Now you can see we've got all of our independent variables, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, what is this, 14 of those, and our target variable is the G3 score, which is the person's total grade throughout the entire year. So let's go ahead and split those up. So x is going to be data.drop, G3 and axis equals 1. And we're going to copy that. And then y will be G3. And we'll do a copy here. I just find that using this copy, it's not always necessary, but it causes a lot less warnings. It's just easier, a lot less trouble if you go ahead and use copy. And we've already got x and y. Now this has been cleaned and it has been set up. But we want to eventually test on completely unseen data. So what we're going to do is split off a test set. And we're going to use train test split over here to do that. Look down at how it comes out. It comes out x train, x test, y train, y test. Okay. So x train, x test, y train, y test equals train test split x and y. Let's see, what do we want our split size to be? How about 10%? And the random state, which you should pretty much always set here because you want to be able to make your results happen again. You want to be able to replicate everything. Random state will be equal to 1. Now I want it to print x train shape and y train shape. Then I want it to print the x test shape and the y test shape. And just make sure that that all works out. What happened? Split. Oh, sorry. This should be test size. There we go. Alright, so we have now 40 of our 355 observations that we're saving to as a test set. And that is small. It's perhaps a little too small, but I'm not too worried about it. Maybe we can make it a bit bigger. How about 0.15? There you go, 60. We'll use 60 observations as a completely unseen test set. Alright? Now then, let's fit OLS. We'll fit an OLS model here. OLS model is going to be a linear regression model, just like that. And we can go ahead and fit it to x and y, simple as this. Now let's see what comes out there. OLS model. Of course. Dot, what do we got? Coef. We got our coefficients here. Now, are those the same as the stats model's coefficients? Let's go have a look. I'm getting 6.97. Doesn't exist. Oh, we need to add fit intercept equals true. If you look over here, fit intercept. Bam. How about we just see how many coefficients it made? It made 14. So this is not telling us our intercept, okay? There's the intercept. 6.97, which it is here, negative 0.03, 0.84. All right, so this is giving us exactly the same coefficients. There is just no way to print it off in a nice table like we did with stats models earlier, even though it is exactly the same model because they're both fit using ordinary least squares. Now it's the next one, SGD regressor, stochastic gradient descent model. How does that sound? Call this SGD model. Now, I'm not tuning any hyperparameters on these because I think we want to just kind of compare them out of the box. You can add an L2 or L1 penalty. L2 is a squared Euclidean norm, which is the ridge penalty, and absolute norm is L1, or you can say, you know, a combination of the two, but we're just going to leave everything the way it is, okay? We're just going to leave everything the way it is. Standard, completely black box, out of the box SGD regressor. I'm going to fit it to X and Y. There it goes. I should be able to pull out coefficients here. You can see that they are different, right? Look at that. Significantly different from the OLS version. As is, of course, the intercept. So we're definitely going to get different results here. Oh my gosh, I have been doing this wrong. We don't want to fit it on the whole thing, just the training parts. Let's go back and just fit it on the training parts. We will get different answers because we're fitting only on the train parts. There we go. That's much better. Now let's do ridge regression. Now for the ridge regression, we have this, they're calling it alpha, I call it lambda when we talked about it, hyperparameter that we are going to want to tune. And we're going to use the grid search CV to do that. But let's just make the model first. Ridge model equals ridge. How's that sound? Okay. And we can't fit it yet because we want to do the grid search. So let's call this ridge underscore grid search. Well, we'll need a parameter space. And this needs to be a dictionary where we have the name of the thing, which is alpha. The name of the parameter here, alpha. Okay. And let's do something like a log space that goes from -3 to 2 and go 5 steps. How's that? Let's see what that actually looks like. So if we have this log space, what this is actually going to give us is it's going to start with 10 to the -3, okay, then 10 all the way to 10 to the +2, and it's going to take 5 steps. 1, 2, 3, 4, 5. See that? So this is 0.001, and this is 100, and then you've got 3 of them equally spaced in between. Does that make sense? And that's what we're going to do here. This will be pretty quick. Let's actually make it 10. Why not? That'll get us a better thing. Now, the thing to look out for in a grid search CV, like we're about to do, is the more of these you have, the better the more likely you are to actually fit the best combination of hyperparameters. We only have one hyperparameter here, but if we had two, well, we'd have 10, and then we had another 10. That's a total of 100 possible combinations. So that gets big really fast, and it can take forever if you have a whole bunch of hyperparameters you're trying to tune at the same time. Since we only have one hyperparameter, I'm going to go ahead and say, there's 10 different possibilities for that hyperparameter. This is what they are. And we're going to try one with each one. So this takes grid search CV. It takes an estimator, which will be our ridge model, and a parameter grid, which we just made. And then this scoring equals none. It's going to automatically use whatever the scoring function is for the estimator. Which I believe it is the mean squared error here, although I could be wrong about that. There we go. It's using r squared. Interesting. Okay, good. So we have here, we'll need an estimator, which is our ridge model, and then we need a param grid, which is the ridge params. And go ahead and make that. We'll fit it here. Whoops, gs.fit x train x y train. And let's go ahead and give it a random state. 2. How's that sound? That doesn't have a random state. Alright, whatever. We'll just get rid of the random state. I thought I had one. That's fine. So what this did was it fit 10 different models, okay? One with each version of alpha, each value of alpha. And then if you look in here, sorry, gs.best model, best estimator, there we go. Then it'll tell you alpha equals 100, which is the highest one. We don't want that. Okay, so let's go ahead and raise this. We'll go from 3 to -2 to 3. And we'll try it again. There. Alpha was somewhere in the middle, which is fantastic. Okay, and we're going to save this as the best ridge model. It's going to be our best estimator. And let's see what the score was. Best ridge model, or best GS, ridge GS, that's my bad. And its best score was 0.069. Not bad. So we've got our best ridge model. It's right here. It has an alpha value of 77 point something. $77.42, which I don't see here, but it's there somewhere, I guess. And that's all good. Let's now do a lasso model. And we'll need lasso parameters as well. Now for lasso, which should be this one, it is also called alpha. We're going to do exactly the same thing as we did before. So there's alpha. We're going to do np.log space, and we'll do -3 to 2 and 10 of them, just as we did before. Now this is the lasso grid search. And go ahead and fit the grid search to the training data. There you go, tells you what it did. We'll pull the best estimator out, see what that looks like. Now this one's got alpha is 0.04. This one, right there. And let's see what its score was. estimated score slightly lower than the ridge score. We'll see what that means later. Now we're going to do an elastic net. And we'll need to actually look at what the parameters are for this. Yeah, should be this one. There we go. So we've got an alpha, but what is alpha? It is a constant that multiplies the penalty terms. So it looks like this is the same as the lambda. Now the L1 ratio, this is the mixing parameter. Alright, so if L1 is 0, then it's purely ridge. And if L1 is 1, then it's purely lasso. So we want to do somewhere in between. So we have two hyperparameters here that we're interested in. We're interested in alpha and we're interested in the L1 ratio. So since this one has two hyperparameters that we're interested in, I'm still going to do 10 probably for that. And let's see, what was the other one called? It was called L1 ratio. For this one, I'm going to use a lin space, okay, a linear space. This is what this is going to look like, a lin space from 0 to 1, and I want 10 of them. How does that sound? Okay, so it's going to go from, well, I don't want that. How about 0.01 to 0.99? There. Alright, I don't want pure ridge or pure lasso because I've already got those. Right? So let's go use a lin space from 0.1 to 0.9. This is great. And we'll use 9 of them. So I've got 10 options for alpha, 9 options for the L1 ratio. So this is actually going to fit 90 different models. All right, one for every single combination of those. So this one, it very well could take a while. Elastic net grid search. Fit that to the training data. There we go, that didn't take too long. And let's see what the best parameters were. Best parameters were an L1 ratio of 0.1, all right, and an alpha of 0.166. So the alpha wasn't so bad, it's somewhere in the middle, but the L1 ratio was all the way on the left side, and again, you really don't want that, because that means you're unlikely to be getting actually the best ratio. So let's do this again. I'm just going to change it to 0.01. So our new stuff that it's going to look for is going to go a little bit under 0.1. Let's change this. Let's have it only go to 0.5. There. So we've got at least 2 options less than 0.1. See how that works. And our best estimator, again, it's choosing the lowest possible value. So it really looks like maybe just having the L1 ratio being 0 is the best. And an L1 ratio of 0, right, refers to the ridge regression. Very interesting. Ridge regression often is fantastic, so I guess it works. Best elastic net model. I'm just going to save it as this one. Bam. Now, I want to compare the models. No, I don't. I want to fit best models to the whole training data. That's what I want to do. So with the OLS model and the SGD model, we've already done that, fit it to the entire thing. But since these other ones where we did the grid search, there they
are fit to a subset of the models. Does that make sense? So I just want to take their best parameters and refit them to the entire data set. So my new ridge model is going to be ridge, and my parameter is going to be, so I want alpha is equal to ridge gs dot best params alpha. Okay. Knew I wasn't crazy. Oh, I forgot to fit it. That's what's up. Ridge model.fit to the entire thing, x train and y train. Have a look at these coefficients here. Look at that, that's interesting because these are actually somewhat close to these ones, aren't they? Not bad. Okay. Now then, I want a new lasso model where the alpha is equal to this, and then I want to fit it to the entire training set. Check for typos and try to run it. There we go. Look, it has pushed this one all the way to 0. Here it's just close to 0 with the ridge regression, but here it's been pushed all the way to 0, and with OLS it was very close to 0 as well. This is the thing that either makes lasso great for your problem or makes it not work so well for your problem. The fact that it will push a coefficient all the way to 0. Interesting. Now we'll need a new elastic net model. And we need alpha is equal to elastic net grid search the best params alpha. And the L1 ratio is going to be equal to the elastic net grid search best params. No, that's right. L1 ratio. And we want to fit that to the training data set. There we go. And we want to have a look at the coefficients. And there those are. And you would expect these to be pretty close to the ridge ones because our L1 ratio was really close to 0. You can see that it is pretty close. It's not exactly the same, but it's pretty close. So now we've got our best models fit to the entire training data. Let's go ahead and pull up the coefficients for the OLS model and the SGD model there as well. We can look at how they change. This one is perhaps the most different from the others. Look at this. All the other ones, it's close to 0 for that first column, but here, 0.42. Very interesting. Now we want to predict on the test data set. So this is going to be OLS predictions equals OLS model dot predict x test, and then we want the SGD predictions on x test, and we want the ridge predictions, and we want the lasso predictions, and we want the elastic net predictions. Alright, we've got them all now. And, well, what should we do? Let's go ahead. Does plotting make a lot of sense? Not really, no. Alright, let's get a way to score them, shall we?
So from sklearn.metrics, let's import mean squared error. How's that sound? And what we're going to do is we're going to compare mean squared errors. Okay, OLS MSE is going to be the mean squared error of y-test, the true value, and the OLS predictions. And SGD MSE is going to be the mean squared error of the y-test and the SGD predictions, and so on. Now let's make us a list. We're going to call this models, and that is going to be OLS, SGD, Ridge, Lasso, and Elastic Net. And then let's make us a data frame. See what this looks like. Yeah. It needs to be in a list here. Alright. Oh, I know what I want to do instead of this. Way better idea. Let's go with this list, alright, of OLS MSE, of SGD MSE, of Ridge MSE, Lasso, and Elastic Net. Let's have the index be models. How's that? Now let's have a look at that. I guess we should have columns now. Alright, so you can see our mean squared error was actually lowest for the ridge regression on the unseen data, which is what we kind of expected. We expected a regularized linear model to perform best. And now you can also see that Elastic Net was very close. That's because our L1 ratio was almost 0, which if it is 0, then that is the same as Ridge. Lasso actually performed worse than OLS, which is interesting. And again, sometimes Lasso is great, and sometimes it is really not great, and there's not a whole lot of in between. All right, and you can see that here. Last thing I want to do is I want to compare maybe the distribution of the predictions with the actual distribution. Is that all right? So let's go ahead and do this. Let's say sns.distplot. You know what? Let's give it a fig size first. Plot.figure fig size is going to be 20 by 8. I just like that size. I think that's a good size for a figure. And then we want a distribution plot of y-test. Let's have a look at that. Should look nice. Alright, so far so good. Very nice. Now let's add to it this plot of OLS pred. Make sure that this looks good before we keep going here, and it does. We're going to need a label or something. This way. Alright, let's go ahead and add the rest of those. kind of too much for us to really tell what's going on, isn't there? Let's only do a few of these at a time. So this is going to be the actual values, the OLS, and the stochastic gradient descent. So you can see that it looks like stochastic gradient descent is actually catching the distribution of the y values a little better than OLS, even though OLS had a lower mean squared error. And I think part of the issue is that nobody's really getting over here or over here. But OLS is getting a little closer to being up here, so maybe that's why it ended up with the lower MSE. Now neither of those actually performed all that well, so let's leave them out and let's look at the rest. Yeah, look at this. This is a little hard to see. It's easier to see in these KDE lines here, but you can see that elastic net and ridge are very similar, and they're really catching the center, okay, of the thing. You can see that their center is a little bit to the left of the lasso center and a little bit closer to the center of the actual values. So that's probably why they're getting lower MSE than lasso. However, lasso looks really, really concentrated right here, and that's because it kind of threw out one of the independent variables. It set that beta equals 0. So it just kind of got rid of that entirely. So it's very centered, and it's a little higher than center. So that's why the ridge and elastic net are doing better, is because they're closer to the same center, and they're like just kind of, the concentration is different, and that works out nicely. So we have then compared these 5 different ways of running a linear regression, and you can see why something with regularization, especially ridge regression, is so popular in machine learning circles. It's easy to explain, it's easy to understand, it's easy to build, there's a closed form solution, and it tends to perform really well on unseen data. So now let's talk about applying these linear models in the realm of finance. And specifically, we're going to talk about linear factor models. Now, a lot of quantitative trading relies on the assumption that y, which is returns, is equal to f of x, and x in this is some risk factors. So it's saying that the returns are defined by some function of the sources of risk for that asset. And a lot of machine learning and finance is actually about predicting those risk factor values. And a linear factor model is just an assumption about the function of the form of that function f of x. And it just says that f of x is a linear function. So we have y equals f of x, which is equal to alpha plus beta 1 x1 plus beta 2 x2, and so on, all the way to beta n xn, and x's, of course, are just sources of risk for that particular asset, whether it's a stock or a currency, whatever. Now, alpha in this is super important because it is the return that is not based on risk. Even if all of your risk is 0, you will still get a return of alpha. So when people talk about how they're looking for alpha, or they have a high alpha, or they've captured alpha, that's the alpha they're talking about. Well, when we have fewer factors than assets, decomposing asset returns into factor returns means that we actually need less data to find the covariance matrix that we can then use to optimize our portfolio. And the coefficients, right, all those betas, they represent the change in returns for a 1-unit change in the risk factor, which we can then use to quantify our risk and take appropriate hedges. Next, with statistical inference, we can determine if factors are actually useful, and we can, find the value of adding additional factors to our model. And using other, predictive analysis or model diagnostics will let us check the predictive value of factors in a different way. And that kind of model diagnostics, that works in a lot of different kinds of models, so it's definitely something you want to be used to doing. Now, a factor model will also allow us to measure portfolio performance relative to a benchmark. And then we can use the model to determine if the performance of our portfolio is actually due to skill, something like asset selection or market timing, or if it's really just due to risk tilting, which could have been achieved by a passive fund. We are now going to talk about two very important factor models. The first one is the capital asset pricing model, CAPM. Most people will talk about it. And I'm not going to lie, I was confused by this for a long time. But the intuition is really not that hard. The first step of intuition is that every investment gets at least the risk-free rate, or investors would always invest in risk-free assets. And the question that goes along with that is, then how come investments lose money? And we'll see how that comes out of the model later. The second is that you cannot diversify away the entire market. The question that goes with that is, so how do market neutral strategies exist? The third bit is that we don't know if markets are efficient. And the model looks like this. We have the expected return from asset I is equal to the risk-free rate plus the market beta times the expected market return minus the risk-free rate plus alpha I, alpha for that asset. Now, if markets are efficient, then alpha would already be priced into the asset. So efficient markets implies that alpha equals 0 every single time. But a lot of research has been done, and alpha is not always equal to 0. And there are two issues here. First, markets really don't appear to be efficient. All right, that's good for us as quants because our job is really to harness those inefficiencies. And second, well, why should there be only a single factor that explains asset returns? I mean, when you're valuing anything else, we're going to consider multiple factors. I mean, let's think about buying a car, right? You're not just going to consider the market price of the car, right? You're going to ask yourself all sorts of questions, like you need to consider the size of the car. You'll want to consider the whether you're getting a good deal probably on the car. You might want to consider how much it costs to drive that car. Is it good on gas? Are you going to have to fill up all the time? Is repair going to be very expensive? And you might also want to look at resale value. Or perhaps, is this car still going to be nice, in 5 years? So since you're asking all those questions about a car, why wouldn't you ask the same sort of things about a stock? And that's where the Fama-Macbeth factor models come into play. So there's a 3-factor version and a 5-factor version. And these kinds of questions, they also led us to arbitrage pricing theory, which is going to allow multiple factors, but it doesn't really specify what they should be. And that arbitrage pricing theory is what really leads us into the Fama-Macbeth models. Now there's a 3-factor version or a 5-factor version. So Eugene Fama and Kenneth French, they started by adding relative size in market equity and relative value in book value versus market equity to that CAPM model. So their 3-factor model looks like this. We have the expected return from asset I is equal to alpha plus beta 1, which is the market beta for that asset, times the expected market return minus the risk-free rate, plus the risk-free rate that every asset gets, plus beta 2 times the relative size, plus beta 3 times the relative value. And after further research, they also added operating revenue, which is defined as the revenue minus costs divided by their assets, and investment, which is defined as the total investments over total assets to the model. So their 5-factor model actually looks like this. We have the expected return from asset I is equal to alpha plus the risk-free rate plus beta 1, which is the market beta, times the expected market return minus the risk-free rate, plus beta 2 times the relative size, plus beta 3 times relative value, plus beta 4 times the operating revenue, plus beta 5 times investment. In this portfolio building regression, we're going to start off with some number I assets, all right? And each is going to have its own data frame that looks like this. Now, each row here represents a point in time, probably a day or a month or something like that, and each column represents a factor, and this column at the end is returns. And these will have values. The value of factor 1 at time t1, factor 2 at t1, and so on, the return at time t1. Now we really have two dimensions that we want to do linear regression in to get to our factor premiums. And we're going to have one for each asset over the time dimension, so we're going to regress this way. All right, this is going to be one regression where each column is an independent x variable, and the returns is going to be the y. And then our second dimension is going to be time-wise across all of our different assets. But look at this. Let's look at this first one. We're regressing this way. Okay, so our regression here is actually going to be r sub I. This is the ith asset. Okay, is equal to beta I fi plus epsilon. Where this here, these are the factors. And this right here, this is the factor premiums. And then in the next dimension, going this way, we're going to treat every single asset at once, okay? And we're going to treat, we're going to regress all across the factors, and we're going to end up doing this. The returns at time t is equal to beta times lambda. Okay, where this one here, this is, the beta is still the factor premiums, but the lambda is actually our risk premiums. And now that we found lambda, we can actually draw statistical inference using this test statistic, t here. This is a t statistic, not time, is equal to lambda j over, this is sigma, the variance of lambda j over the square root of t. Now, as you can probably guess, if t is big, meaning that we have a lot of data, because this capital T is the total number of time steps that we have data for, if t is big, then this whole denominator is going to be small. But we usually don't have a large sample of representative data. That's where we get stuck, is representative data. And estimating mean returns using this model usually ends up with a wide margin of error. However, estimating the variance of returns is typically easier, and adding a small amount of data can actually have a big impact on our error there. And this whole procedure that we just talked about is called Fama-Macbeth regression. And now we're going to head over to Python and look at doing Fama-Macbeth regression in action. Now we are going to build a linear factor model in Python. Specifically, we're going to build the Fama-French 5-factor model. And we're going to be using all OLS regressions. That's why we just need stats models here. And we're actually going to use, here's what we're going to do, is we're going to go through this whole thing manually, and then we'll show you another function from this linear models package that will actually run this Fama-Macbeth regression automatically, very easily. Now, Kenneth French has some great factor data available from his website. There's a link down here, and you can pull it in through with the Pandas data reader API super easily. Now, in the five-factor model, we have, of course, five factors. The first of which is small minus big. This is the difference in average return between a portfolio of small cap stocks and a portfolio of large cap stocks. And then we have high minus low, which is the difference in average return between a portfolio of value stocks, which have low price to book ratio, and growth stocks, which have high price to book ratio. Then we have robust minus weak, which is the difference in average return between a portfolio built of stocks from companies with high operating profitability and a portfolio of stocks with relatively weak operating profitability. We have conservative minus aggressive, all right, which is the difference in average return between a conservative investment portfolio and an aggressive investment portfolio. Less investment versus more investment. And then we have RM minus RF, which is the excess return on the market. It is value-weighted return of all firms on the market in month T minus the 1 month T-bill rate. And that 1 month T-bill rate is standing in as the risk-free rate. Now I've included a link here in this notebook that you can get to in my GitHub, and it's going to tell you more about the factors. It is by Fama and French, published in 2015, about the factors, and you guys can read all this, right? And there's more to how the factors are actually calculated, and you should definitely go through all of this and read both Fama's website or French's website. Yeah, French's website, and through their paper, and kind of learn more about how this works. But our next step is to get the data. We can pull that in on Fama French website. It is just called this right there. So we're going to start reading it in 2000. We're going to end in December of 2020. And we're just going to pull it in, separate it out. This is what monthly factor data looks like. There's 252 values. We have the market return minus the risk-free rate, small minus big, high minus low, robust minus weak, conservative minus aggressive, and then the risk-free rate, which we said is the 1 month T-bill rate. And we have 21 years of factor data, okay? There are no missing values, everything looks good. And when we describe them, this is just to kind of see what it looks like a little bit. You can see the means pretty small, and everything from there. Right here I'm just checking to make sure there's no missing values. Now we will need portfolio return data, which is also available on Kenneth French's website. And we're going to get returns for 17 different industries. You can see what those are here: food, mines, oil, clothes, durable goods, and so on. And we'll just look at a description of that real quick. Not a whole lot to talk about there. Looks good. Now, I have a bunch of data that was downloaded before. I'm pretty sure I made a video about getting it. I will make sure, and if I didn't, then I'll upload one soon, because it was like you can't do any of this without this data. So I pulled in the prices and stock metadata here. I got the sectors from the stock metadata. Okay, this has just information about all the different stocks in it, and I'm pulling the sectors out. And then prices, I'm just keeping the prices for stocks in those 17 sectors. Then I'm resampling to monthly returns, changing them to a percentage, all right, by multiplying by 100. And I'm just dropping anything that's missing, all of it. And look at here, I have 218 entries from February 2000 to March 2018. So we've lost a little bit of data, but that's fine. There's also 1,229 stocks that we're looking at. So we have way more assets than factors. We have 5 factors, but we have over 1,000 stocks. So that's why it's good to decompose stock returns into factor returns when you're trying to do portfolio optimization. Now we just want to make sure that it lines up correctly. We just want to make sure that everything has the same values on the same days. Does that make sense? So we'll get the excess returns by getting our returns up here. We'll get the excess returns by taking our returns and subtracting the risk-free rate. Because the Fama-French model actually it explains excess returns, not just regular returns. Now next we're going to take the excess returns and we're going to clip off the top and bottom percentiles, the 1 percentile and the 99. And we're just going to clip it off there so that we don't have outliers messing everything up. And that's part of having something high variance like linear regression. Those outliers can make a huge difference, and since you don't want them to mess up your model, you can just clip it off and use good risk management, all right, to eliminate or limit the effects of outlier events. Now we're ready to do Fama-Macbeth regression. And step 1, of course, is time series regression to estimate factor exposures. So we're making an empty list of betas. We need to go through every industry. And we're going to do an OLS regression where our X variable is the monthly factor data, which we need to add a constant for the intercept for alpha, okay? And then our Y variable is the monthly return by industry. And we're going to drop the intercept from the final one. Now, as you can see, each of our 17 industries, there we go, had these betas. Now then, step 2 was a cross-sectional regression, okay, to estimate the factor premiums. So now that we have the betas, we need to do the second part of our regression and get those lambdas. So we're going to make an empty list of lambdas and go through month by month. And we're using all of the industries, all 17 of them. And our X values this time are just going to be the betas from before. And the Y values this time are going to be the monthly returns. And we're just going to stick those all into our lambdas list. And when we get it out, we can see these factor premiums. So if we look at the factor premiums over time, like the average at least, we can see that robust minus weak had the highest factor premium, which means, let's see, it's about 0.72 maybe, something like that. Which, what that means is that companies with robust operating costs outperformed companies with weak operating costs pretty severely. And we can see that exposure to the market, this one, the excess return on the market was actually very important, which is interesting. A lot of stocks are very correlated with the market and have relatively high market premiums, like this. We can see that these three, high minus low, the risk-free rate, and conservative minus aggressive, didn't really matter, which is cool. And then this one, small minus big, was actually negative, which means that relatively big corporations did better than relatively small corporations between the years, between February of 2000 and March 2018. Then we can look at how those factor premiums change over time. With this plot, you can see how they're pretty crazy. Look at the one for the risk-free rate. We would expect that to be close to 0 because why does that matter, right? It didn't have a beta at all in our model, so it's close to 0 the whole time, which is good. You can see that even though robust minus weak ended up being the highest on average, it follows a pretty wild path. And small minus big as well. You can see in the early 2000s, small and big, there wasn't much difference between the two, but especially after that market crash and stuff in 2008, 2009, big corporations did a lot better afterward. Now this has just separated them out so you can look more at each of them individually. Now that's Fama-Macbeth regression, where we actually did it all ourselves. But like I said, this linear models library or package for Python has a super easy way to just do it all at once. So you can get your model, which is called linear factor model. You get your portfolios, which is going to have the monthly portfolio data that we made, and your factors, which is going to have the monthly factors, and then just fit it, and then print the results. And it returns a table, very similar to the stats models OLS table for the whole Fama-Macbeth regression. Now this is on average for all of the industries over the entire time. And you can see here small minus big was almost negative 0.8, which we saw in that bar plot there. And robust minus weak was about 0.75, which we also saw in that bar plot. And look at these p-values. The only one that it said was really super important, significant at a 0.05 significance level, which is kind of arbitrary anyway, was robust minus weak. But these actually had relatively low p-values as well, the excess market returns and small minus big. The other ones didn't really seem important. Now if you print the results full summary, that's going to give you a lot more information. So here's the average, okay, risk premia estimates here, average lambdas. And then a little further down, the coefficients for the food industry. Okay, your alpha was 0.04 there, or it could have been 0, we don't know. For the mines industry, again, alpha is not very important, but super exposed to the market. Also, big mines did way better. I'm sorry, small mines actually did way better. Interesting. Further down, oil, you can go through all of these. There's going to be 17 of them. I'm just looking to see if any of them had a significant alpha. We're getting closer with alpha, with the, what is that, construction maybe? Or steel. Oh yeah, this is close. Something to do with machines? I'm not real sure. Or cars. Cars almost had a nice significant alpha. You can see what all of that does. And then down here I just printed off the mean lambdas so you can look and see that they are the same thing that you're given by this full summary from the linear models. Super easy way of doing it. And that's how you do Fama-Macbeth regression in Python. We did it both ourselves and using the linear factor model function from the linear models library.
Congratulations. That was about 3.5 hours on linear regression. You guys, you did it all. You talked about the strengths and weaknesses of linear regression. You talked about several different ways to fit the model. You did OLS for some statistical inference. You did regularization and shrinkage, and you learned how to apply it all with Fama-Macbeth regression in finance. So I hope that you learned something. If you have any questions, leave them in the comments. If you did learn something, I'd really appreciate it if you hit the like button. And if you want to keep learning, go ahead and subscribe. And I'll see you guys next time.